Okay, guys, welcome to part 2 of complex numbers, the trig form. So in the last lecture, we showed that we can rewrite a complex number into something that's boring and dull. Into something, sorry, wrong way. I'm going from something that's boring and dull into something that is exciting and cool, right? I know what cool things are. I'm a math teacher. I know. So this is what we found where, what do we know? We know where r is the square root of, it's the magnitude of that complex number. So you might be asking yourself, why would I ever want to actually do this other than to get a grade in the class that you're taking? Is there any reason why mathematicians might want to do this? Or not just mathematicians, we use stuff like this in a lot of other disciplines. I don't know, that might be reaching it a little bit, but so what this form can be useful for are the next kind of 3 ideas that we're going to do. So first of all, if I were to multiply some complex numbers, sometimes putting it in a form like this makes it easier. Division also of complex numbers can be quite complicated sometimes, right? Because when we divide complex numbers, we usually have to multiply by the conjugate of the denominator. So, I mean, who wants to do that? When we could put it into the trig form of a complex number and make it a little bit easier. And so I'm going to show you this, and then let's write this down, and then, well, actually, let's just do this really quick and then we'll write it down. So I'm going to show you kind of the motivation for how to get this formula that we're going to get. I'm going to give you this formula on the test, don't worry. I'm not going to prove it for you for division. But let's just say, let's consider 2 complex numbers. So these numbers are going to be different. So I'm going to say the first number is given by r sub 1. So r sub 1, again, that's going to be the absolute value of the first complex number. And then it has some angle theta that's related to it, right? And we'll just call that theta sub 1. We just want to use kind of the same notation, but I want to be clear that these are 2 different numbers. They're distinct. I guess they could be the same number. This would be true for the same number also, but I want to express that they don't have to be the same number. So this represents, maybe like some number a sub 1 plus b sub 1 I, and this maybe is some other complex number, I'm going to erase this so you might not put it in your notes, b sub 2 I, okay? So that's what we mean by that. Whoa. So let's see what happens when we multiply these together. So if I multiply them, let me show you. So I'm going to take this r1 times r2, I can just kind of multiply those together. So I'm just rearranging, I'm just using, aren't you glad that we're working in a system where the commutative property of multiplication is true and the associative property? And apparently, you can hear that. I think people know when I'm recording a lecture in my office, and like every single person that has a cart in the college just starts pushing it on the brick hallway. I've come to believe that this has to be true. I know it's not actually true, but still that's what it seems like sometimes. Okay, so we're going to multiply these out. So this r1, r2 is just going to hang out and be r1, r2. And now I'm going to FOIL this out. So I'm going to have cosine of theta 1, cosine of theta 2. So that's just cosine theta 1 times cosine of theta sub 2, right? That just are 2 different angles. If I do outside, I get plus I cosine theta 1 sine theta 2. Inside, I get plus I sine of theta 1 cosine of theta sub 2. And then if I do last, this is exciting. So if I do last, I'm going to just save myself a step. I get I squared, right, times sine theta 1 sine theta 2. But what is I squared, you guys? Remember, I squared is -1. So what I actually get is I get minus sine of theta 1 sine of theta sub 2. And now if I kind of group some of these together, okay, so notice, let's take everything that does not have an I and put that together. So the cosine of theta 1, cosine of theta 2, right, minus sine theta 1, sine theta 2. Those guys don't have an I, so I'm going to group them together. And then the stuff that does have an I have plus I times what would I be left with? Let's put the sine one first, just because it has the theta sub 1. Sine theta 1, cosine theta 2 plus cosine theta 1 sine theta 2. Oh my gosh, you guys. I bet you are so excited right now. I am too, because I know that you, I mean, don't do it in front of your friends. I understand you got to keep your facade that you don't think math is cool, but look at what this is. This right here, if you remember, of course you remember, but just in case you forgot, remember the cosine of alpha plus beta, right, was cosine alpha, cosine beta, and then the opposite sine, S-I-G-N, which was minus sine alpha, sine beta, right? This is the sum formula, you guys, for cosine. So this whole thing right here, this becomes the cosine of theta 1 plus theta 2. Isn't that so cool? I just love it. I just love it. I'm not gonna lie. I love it. I think it's so awesome. And then over here, let me get a different color that might show up well. If I look at this guy right here, I know it's exciting. The sine, remember, of alpha plus beta, right, was sine, cosine, cosine, sine. So it was sine alpha cosine beta plus, and then we just switched cosine alpha sine beta. And this, my friends, is the same thing as that. So this is sine of theta 1 plus theta 2. This is such a cool result of writing complex numbers in their trig form. Isn't that neat? So this whole thing right here is replaced with this. This whole thing right here is replaced with this, and then we have the R1 times the R2. So let's write that down a little bit more formally. Isn't that neat? I just love that. When I was kind of deciding, prepping for this lecture, hold on. Let me write this down. I was kind of wondering if I should actually prove it to you or not and just state the formula, but the proof of it is just so nice and easy to follow. So it's kind of a really cool way for you to see maybe where like a sum formula comes in or a difference formula comes in that is actually quite useful to us, and we actually use it. Okay, so given complex numbers, given the, whoa, settle down there. Settle down there, pen. Given the complex numbers, so we have two complex numbers. Well, actually, I'm not going to write all that. You guys know they're complex numbers. I'm just going to write out the result, okay? So if I have two complex numbers, R1 times cosine of theta 1 plus I sine of theta sub 1, right? That's the trig form for my first complex number. If I'm going to multiply that with R sub 2, which is cosine given by this, given by the complex numbers given by this, R2 times cosine theta 2 I sine theta 2. If I multiply those two, here's how I can multiply them. I don't have to go through and I don't have to FOIL that all out and combine like terms. All I do is I multiply their absolute values. So I take R1 times R2, and then I multiply that times the trig form, which ends up just being cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. This is so neat. I recognize that you're probably not going to appreciate this as much as I want you to, but it just is, when you're working, you know, with numbers, you're working with groups of things in mathematics, when stuff like this happens, it just is so, it's so great. I don't know how else to say that. So let me show you kind of why this might be useful for us. Okay, so let's look at a quick example. Find the product. And we'll look at two different numbers. Let's see, let's find the product of, and we don't have to beat this horse, you know, so I'll do one example and call it good, and you can look at the fun sheet. The fun sheet has other examples of it. So here's my first complex number. Okay, so 2 times the cosine of 2 pi over 3 plus I sine pi over 3. And let's say 8 times the cosine of 11 pi over 6 plus I sine of 11 pi over 6. And then let's write the answer in standard form. You can't always do that, but I think we'll be able to on this one, right? In standard form. So anytime I say standard form, what I mean is the A. I don't want it in trig form, okay? It's the A plus BI. All right, so I'm multiplying these two numbers together. So what are my r's? My r's are the 2 and the 8. So when I take their product, I'm going to take 2 times 8, so that's 16, right? And then I'm going to have the cosine of, and then I just do what this kind of theorem tells me right here, I just add them together. So I'm going to have 2 pi over 3, and we'll get a common denominator here in a minute, plus 11 pi over 6, right? Plus I sine of 2 pi over 3 plus 11 pi over 6. So cool. I just love it. That's it. I know that that's how we multiply them because I proved that to you. So this is going to be 16. Okay, guys, let's work on our common denominators. So this needs a 2 over 2, right? I'm going to multiply the top by 2. That'll give me 4 and 6 on the bottom. So what am I going to get? I'm going to get 15 pi over 6. So at 15 pi over 6, if I divide everything by 3, I get actually 5 pi over 2, right? Plus I sine of, this must be the same thing, pi over 2. And then if I want this in standard form, let's see where 5 pi over 2 is, right? Here's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So this is exactly the same as the cosine of pi over 2 plus I sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So I just bring that all together and I get 16i. And that's my final answer. Isn't that cool? I love it. Love it. I love it. I just think that's so much fun. That's so neat. It's neat, you guys. All right, so that's multiplication. Simple as that. So you just add the angles, right? Multiply your r's together. Let's talk about what happens when we divide. So I'm just going to write this down, and then I'll let you, look in your book, or what would be a fun exercise that you guys should do. Well, this one's not so easy. I was going to say maybe you should just try and do it kind of like the way we did the multiplication, but actually it's a little bit more difficult than that. But I'm going to not do the proof for this one. So if I divide two complex numbers, it's going to be quite similar. So if I take the cosine of r1 times cosine of theta 1 plus I sine theta 1, so that is my first complex number, and I want to divide it by my second complex number given by the same kind of thing. You would hope that things would be similar, and actually they are. So the great thing about this is it's going to be very, very similar to our multiplication one. So I'm going to take r1 and I'm going to divide it by r2. I mean, that's kind of given right there, right? But then what I end up doing, instead of adding the angles together, we'd subtract them. That's really neat. I kind of love that. I mean, that's probably not surprising to you that I love this. So I would do theta 1 minus theta 2. Sorry about that. So same idea as the multiplication, except instead of adding, we're just going to subtract. Isn't that neat? So let's do one example. This is going to be a pretty fast lecture. Or this second part won't be quite as long as some of the other ones. Let's find an example here. Okay, so just for fun, let's convert, let's do 3 minus 3 root 3i all over root 3 minus I to trig form and divide. And then because we started off with standard form, let's go ahead and end in standard form. So this is just kind of a fun exercise. Now remember, if I were to actually divide these, I would have to multiply the top and bottom by root 3 plus I over root 3 plus I, and have to simplify and FOIL out, right? So our goal is maybe that we don't have to do that here. So 3 minus 3 root 3i, let's find the trig form for that. Okay, so I need a couple things. I need my r. So r is going to be the square root of, if I square 3, I get 9. If I square 3 root 3, I get 9 times 3, which is 27, right? So I get the square root of 36, which is 6. And then what else do I know about this guy? So I know it's in the fourth quadrant. I know, if something here, this is not to scale, but I know this is 3, this is negative 3 root 3. If I take the tangent of this, right, I would take y over x, so that would be a negative 3 root 3 over 3, which is a negative root 3. So let's think about this for a minute. So my reference angle then, what angle when I take the tangent of it gives me root 3? That would be pi over 3. Or you know what? Let's do, I know I don't often do degrees. Let's do degrees. So that's 60 degrees. So what is theta going to be? 300 degrees. Okay, so what do I know about this guy right here? This is going to be 6 times the cosine of 300 degrees plus I sine of 300 degrees, right? All right, well, this is awkward a little bit, but that's okay. How about root 3 minus I? Let's do the same thing for this guy. R is going to be root 3 squared is 3. Negative 1 squared is 1. Square root of 4 is 2. Right, and then I know I'm also in the fourth quadrant here. But in this case, this is root 3 and this is 1. So the tangent of theta then would be, negative 1. Negative 1 over root 3. So because root 3 over 1 was 60, now I must have a reference angle of 30. So if I have a reference angle of 30, right, I'm going to have 2 times the cosine of 330 plus I sine of 330. All right, guys. So now I'm going to need more room. So here, what do we have again? Let me clear this out really quick. Okay, so now I have, oh, what do I have? I don't even remember. I have 6 and 300. So I have 6 times the cosine of 300 degrees plus I sine of 300. This is a good way, like if I have you first convert it to trig and then divide, it's a good way for me, just so you know, test you several different things. Do you know how to change a complex number into a trig form? And then can you use the division theorem there? So, okay, so let's look back at what what my division rule was. So I'm going to divide the r's, and then what am I going to do to the angles? I'm going to subtract them. Okay, and then I'll simplify. So I'm going to divide the r's. So this is 6 over 2. I know that's 3, but we're just being kind of showing all my steps here, okay? So I have, I'm going to do this down here. 6 over 2, sorry. 6 over 2, and then what is this going to be times? This is going to be times the cosine of 300 minus 330. Be very careful about order here, right? You guys, order matters. So it's always the numerator minus the denominator. Right? This does matter. So look at what I have here. I have 3 times the cosine of a negative 30 degrees plus I sine of a negative 30 degrees. And so let's figure out what those are, because we started in standard form, so let's go ahead and end. So negative 30 degrees is right here. We're in the fourth quadrant. Cosine in the fourth quadrant is positive, so the cosine of 30 degrees is root 3 over 2. So this just becomes, if I take the 3 through it, 3 root 3 over 2, but then sine in the fourth quadrant is negative, so this just, and it's 1/2. Sine of 30 degrees is 1/2. So I get 3 root 3 over 2 minus 3/2 I. Now, you probably would argue with me, which you might be right. I don't like being wrong, but that it may have just been easier to multiply by the conjugate. And maybe it would have been, but it's not as fun. I'm going to tell you right now, not as fun, because you don't get to convert to trig. So that's how we can multiply and divide complex numbers that are in trig form. All right, we have one more thing to do, and then we're done. One more thing, one more theorem. So the theorem we're going to do is called DeMoivre's theorem. And DeMoivre's theorem comes where, so we looked at multiplying and dividing complex numbers. What if I wanted to raise a complex number to a high power? Okay, so I just want to kind of look at the kind of the motivation for this really quick. But let's say that I was taking, you know, a complex number in trig form, and I was squaring it. So the motivation behind this is kind of interesting. So if I was squaring this, right, look at what I have. I have two numbers. Now I know normally I would just square each one, but if I think of this, because we have this newfound theorem for what to do with how to multiply complex numbers, and you know, you always want to play with a new toy when you get it. Same thing with new theorems, you want to use them. So look at what this says. If I take this number and square it, that's just two complex numbers. So I would get r squared, and then what do I do when I multiply complex numbers, I add the angles, right? So I would get theta plus theta, and then here I'm going to have I sine of theta plus theta. So look at what this is saying then. To square a complex number in trig form, I take r squared and then I multiply times the cosine of 2 theta plus I sine of 2 theta. And we could do that also if I cubed this, right? Cubing it would just be this times one more of them. And what you'll see is you'll get theta plus theta plus theta, so it becomes 3 theta. So DeMoivre's theorem, let's go ahead and write that down. I am not quite sure I'm pronouncing that correctly. I know Spanish a little bit, but French not as much. I'm pretty sure that's DeMoivre. So DeMoivre's theorem, okay, here's what DeMoivre's theorem says. If n is a natural number, then if I have this form of a complex number, okay, the trigonometric form for a complex number, plus I sine of theta, and I wanted to raise that to a natural number, okay? 1, 2, 3, 4, 5, 6, 7, right? All of those. Then here's what we're going to do. So notice where that 2 comes in. It comes in as the exponent for my r. That's going to make sense, right? Because every time I multiply them, I'm going to have that r times r times r. And then what you're going to multiply by is cosine. Where that 2 comes in is it gives you the multiples of theta, which is really neat. So cosine of n theta plus I sine of n theta. So this is not a proof. I did not actually prove this for you. If you can't sleep tonight, you guys, not understanding this, but because you haven't seen the proof of it, first of all, I suggest, you know, some light music or melatonin or something. But if you still can't, is that what it is to sleep? I don't remember. But if you still can't sleep, then you should look up the proof of this. Maybe that would help. All right, so let's do an example of this. So this is DeMoivre's theorem. It's a really cool theorem where you just take that exponent and bring it down. So I'm going to just do one example, and then people, we are done. So you see kind of, we're at 22 minutes already. You see why I split this up a little bit. So let's just evaluate. Let's evaluate, I want to do something really interesting. Let's evaluate something like this. -1 plus the square root of 3i all to the 12th power. Oh my goodness. So normally if I were to ask you to do this, I would be an evil person, and maybe you still think I'm evil. But without DeMoivre's theorem, this is difficult, you guys. I'm asking you to take this complex number here and raise it to the 12th power. I'm asking you to multiply something by itself 12 times, but I don't have to do that with DeMoivre. So the first thing I need to do is I need to change this complex number into a trig form for a complex number. So let's do some work here. So what is r? It's the square root of -1 squared is 1. Root 3 squared is 3. 1 plus 3 is 4. And the square root of 4 is 2. If I look at what quadrant I'm in, right, looks like I'm in quadrant 2. Okay, so here's my theta right here. This is -1. This is root 3. So what is the tangent? The tangent of theta is y over x. So that's a -√3. Okay, so I have a reference angle, and I think it might be easiest to, I don't know, let's stay in degrees. So my reference angle is going to be 60 degrees, so it looks like theta is 120 degrees. Hope I did that right. I think I did. All right, so here's what we got. We got r is 2, right? And then we have the cosine of 120 degrees plus I sine of 120. So while this might not seem like it's going to make things easier, I promise you it will. All right, so I'm going to take this number, 3i, and I'm going to raise it to the 12th, which means I'm taking this number to the 12th. Okay, so I'm going to use DeMoivre's theorem now. Oh man, I should have maybe picked a smaller number, but all right, 2 to the 12th, I can figure that out with my calculator. And then the cosine, let's see, 12 times 12 is 144. So I have 144 and then add a 0 to it. Oh wow, we got to figure out where we're at here. But we can do that. All right, so 2 to the 12th. putting that into my calculator. I know 2 to the 10th is 1024. But all right, so that I probably could have figured that out. 4,096. Okay, what about that 1444? So I could put that into my calculator, or if I take 1440, and if I divide it by 360, okay, 1440 is the same as 4 times 360. So what do I know? This angle is 1, 2, 3, 4. I'm hanging out right there on the x-axis. So that means that the cosine of this guy is that it's coterminal with 360, or it's coterminal with 0 degrees. So this is 1. I'm hanging out on the x-axis, so sine is 0 on the x-axis, because sine are my y values. So this whole thing is equal to 4,096. That's it. This huge complex number raised to that very large power of 12 is equal to 4,096. So you can see where that DeMoivre's theorem is actually pretty useful when it comes to, raising complex numbers to high powers. All right, guys, that was fun. Enjoy.